Welcome everyone, my name is Bogumil Kamiński and now we start the first steps with DataFrames notebook for the DataFrames.jl tutorial prepared for the Julia Academy. In this starting notebook, I will want to show you how you can reproduce a famous Anscombe's quartet plots where we have 4 different data sets containing X and Y axis information of a set of points where, as you can see, for all those 4 examples, the distribution of the data seems completely different, yet they produce the same linear regression as a result. So let us show how to do this using DataFrames.jl. So first we load the required packages, which are DataFrames, statistics, that is a package that is inbuilt into Julia, providing basic statistical function, PyPlot for plotting, and GeoLearn for generalized linear regression models. So we start with creating a matrix containing a data where we will want to store our information. So this matrix is arranged in 8 columns. The columns contain x1, x2, x1, y1, x2, y2, etc. variables. And first, let us see how you can convert such a matrix into a data frame. So the command is to invoke a data frame constructor, and the important thing is that you have to put here the auto argument as a second positional argument, which tells data frames that this matrix should be converted into a data frame using automatically generated column names, which will be x1, x2, etc. Now assume that we do not like those columns names because we know it should be x1, y1, x2, y2, up to x4, y4. That's why let us see how to change the column names into something more following the expectations. So here is a simple expression that creates us the list of column names as strings. So how does it work? We pass to a broadcasted string function, broadcasted because there is a dot here, a vector, so a column vector x and y, and a matrix, a row matrix 1, 2, 3, 4. So because this is a column vector and this is a row matrix, so broadcasting a string function over it creates us, as we can see, all combinations of the past arguments. So we get 8 elements, and I use vec function to get a vector out of it. And now it's easy to change the names of our columns into the newly generated names. As you can see here, I'm using a rename function. Here you can see that I have a bank in the name of the function, and it means that I want this function to operate in place. And so it means that the data frame that I have passed to it will be mutated. And this is a general rule for DataFrames.jl package that, and also in Julia in general. If I have a function that does not have a bank at the end, I will get a new object. If I have a bank, the past object will be mutated. So in this way, I have changed the names of columns in my data frame. I could have also created a data frame with the column names that I liked. I could do this by passing to a data frame construction, the AQ matrix, and then a vector, as you can see here, of column names. So what is important here is that you could see that earlier I have passed strings as column names, and here I pass symbols. And this is a general rule in DataFrames.jl that in order to reference a column, you can use either strings or symbols. So this is very useful because sometimes you would prefer symbols, sometimes you might prefer strings. You can flexibly use both. For example, if I want to extract a y1 column from my data frame, either I can write df.y1, which gets column y1, or y1 as a string. And this gets me exactly the same result. Similarly, I can use a matrix notation to extract this one column from a data frame. So I use a colon to signal that I want to get all rows, and then I use y1 as a symbol or y1 as a string to get this column, and we can see that I get again exactly the same result. So now assume that we would like to reorder the columns of our data frame in place so that first the columns with x-axis come and then the y columns. How to do this? So we will achieve this using a select bank function. So again, bank means that we are updating our data frame in place. And now the question is, how can I easily select all the x columns? Well, the easy way to do it is to use a regular expression. So r and x in quotes means that I am selecting all the columns that contain x in them. In this way, I can perform the operation we want, because the formula here is, as you can see, I select from the data frame df first all columns that contain x, and then column means that I select all the remaining columns. So in summary, this means that first I get the x columns and then the remaining columns, which in this case will be y columns. And as before, I could have used select function instead of select bank function to create a new data frame instead of updating the data frame that I used in place. So now let us check if indeed those columns that I have similar distributions. So in order to do this, I use a describe function, which creates aggregates of our columns. So I want to calculate mean and standard deviation for all columns. So I pass to describe function my data frame, and then I pass a function, which is mean, and the target column name, which will be also mean, the same with standard deviation. So as you can see, all x variables have exactly the same mean and standard deviation, and the same with y columns. There is some variation due to floating point accuracy, but in general, we can see that mean and standard deviation on x and on y axis of all our data sets is the same. Just as an exercise, we can check that equally well I could have passed strings instead of symbols as column names for our data. And we can see that we get exactly the same result. Now, another common requirement is to add an indicator column to a data frame. So we want to add a column that I will call ID that just gives me a row number for each row. So what I did, I assign to an ID column here a vector starting from 1 to number of rows of the data frame. And as you can see, this ID column was added at the end. So similarly to n row, which gives me the number of rows in my data frame, I can use ncol function that gives me number of columns in my data frame, which is now 9 because I have 8 original columns and 1 additional ID column. So now again, just to practice what we have learned, how to move the ID column to the front. Well, I use a select function and first pass ID, column name, and then column as remaining columns. But this time I used select, not select bank. So I expect that the old data frame will not be changed. And in this is the case. As you can see here, the original data frame is unchanged. On simply a new data frame was created. Now it's easy enough to convert back a data frame into a matrix by simply calling a matrix constructor. So matrix constructor, if it takes a data frame, it will create me a data frame, sorry, a matrix out of our source data frame. So now let us move on to creation of the plots. And in this, we will use this matrix constructor. So what is important when making a plot is to make sure that all 4 plots will have the same range on X and Y axis. So here, as you can see, I'm using the select function to select all X columns. Then I convert it to a matrix. I get the extrema of those values, add to them -1 and 1, because in this way I will have the range a bit wider than the actual range of data, so the plots looks nicely. And then I use a collect function to create a vector of it. And we can see that the common range for the x-axis is from 3 to 20. Similarly, I can calculate the common range for the y-axis. As you can see here, the only change is that I replace here x with y because I want to calculate the range for the y-axis. Now we are ready to create a plot, and this is something that is more verbose than the previous examples, but I hope it will be easy enough to follow. So what we use here pyplot package, which is an interface to matplotlib from Python. So if you know matplotlib, you can easily understand this code. So first I create 4 subplots that will be arranged in a 2x2 matrix. I change the layout of those plots in order to improve how they look like. And now I will iterate for I from 1 to 4 to create all 4 plots. So first I create x and y variables that will indicate me the column name for x and y axis. So it will be, for example, if I is 1, it will be x1 and y1 symbols. Then I create a linear regression model here. And you can see that the beauty of Julia in general and GLM package in particular is here that I can use a purely functional way to define it. So this term function tells Julia to generate a model formula based on variables. So I do not have to repeat the variable names as literals. I can pass them as variables, as you can see here. And when I build the model, first I plot the predictions of the model based on the range of data. So as you can see here, I'm passing here limits of the x-axis to create the predictions on the y-axis, and I plot this as a linear regression. So in using an orange color, and then I am adding a scatter plot of our points. And again, as you can see here, I can pass variables as column selectors without a problem. And the following commands are just making sure that the plots look nicely. So I set axis limits, I set labels, and on the top, I will set a title, which will show me the R² of the model and the linear regression coefficients. And as you can see here, all those regressions are exactly the same. So we have efficiently reproduced the plot I have shown at the top, and indeed made sure that all those 4 linear regressions are actually exactly the same. So let us go back to again explain some basic properties of data frames that we have used there. So first of all, you can create a data frame using variables as column names and as column values, and then you pass a pair of column name and column value to create a data frame. So as you can see, X is var1 and X column is from 1 to 3, and Y is var2, and values are from 4 to 6. So as you can see here, in this way, I can have created a data frame with passed both column names and column values as variables, which is quite useful. If I knew the column names up front, so I wanted to pass them as literals, then I can use a simple pattern, column name equals column value, but in this case, I cannot use the variable as a column name. Finally, let us stress the one important feature of data frames. So if you access the column of the data frame, we have shown 2 patterns before. Either I'm writing df.call to get a column call from a data frame, or I can write df and use a matrix notation with a column as x-axis. So the difference between them is that using this notation with a dot, I'm getting a column from a data frame without copying it, while using a matrix notation gives me access to this column, but it gets copied. So now the question is, what if I wanted to use a matrix notation, which is sometimes useful, but I didn't want to copy the column? So there is an easy answer to this. We have a special notation that you use a bank instead of a column. So bank indicates that it's a direct access to a data frame. And if instead of a column I use a bank, I get a direct access to my column in a data frame without copying it. A bank can be thought of as a signal that the operation done here is unsafe because we are accessing an internal column stored in a data frame instead of copying it. And we can check here that indeed using a bank did not perform a copy, because we can see here that V is exactly equal to the column extracted using df.x1 operation. So this triple equals checks us that this is exactly the same object. So it does not check on the contents of the object, but actually the exact memory reference for it. So those were simple rules of indexing in DataFrames. So as you can see below, there is a link to a more detailed discussion of all possible rules, how you can index into a data frame. And I encourage you to check out that page. So this is all for this introductory presentation of how DataFrames.jl can be used. In the next part of the tutorial, we will see how you can read and write data from disk to work with DataFrames. Thank you.